Good morning, everybody.
Good morning.
Good to hear that. That's lovely sounding. It is absolutely a gorgeous fall day. Those of you who are on Zoom and don't live here, you need to come here and see how beautiful it is.
I can vouch for that.
Yep. So just driving in from work, the colors are a riot. And right outside our building, there's beautiful maples growing. So let's enjoy it before the winter comes. But even our winters are beautiful, Doug. So my name is Ranu Jung. I'm the founding executive director for the Institute for Integrative and Innovative Research, which we fondly call I-Cubed-R. So before I introduce you to the speaker, let me once again tell you that we as an institute are driven by purpose to pioneer solutions to wicked problems through a convergence approach that brings together academic, industry, non-governmental, non-profit sectors together in order to be able to have societal impact by creating and deploying innovations at scale. We repeat this every time, but this is a mantra that we are trying to believe in. We have taken on the grand challenge of integrative health with a full understanding that is defined by multiple factors, not only physiological aspects, but economic aspects, social aspects, environmental aspects, all of that. And we are seeking to find solutions from health tech and food tech and cyber tech so that we can create and deploy those innovations that solve the problems. So with that in mind, as you know, this whole semester, we are bringing in trailblazing speakers who can guide us in our journey, speakers who we are looking to for advice and also to learn from. And so it is my pleasure to introduce to you Doug Weber, our speaker today. And as you know from his bio, he's the Akhtar and Bhutta professor in the Department of Mechanical Engineering and Neuroscience Institute at Carnegie Mellon. He received a Ph.D. in bioengineering from Arizona State University. And he had just left when I first went to Arizona State University and we missed each other. And he got his postdoctoral training in the Center for Neuroscience at the University of Alberta. So Canada has kind of rubbed out to him. But we were talking about it, that how long ago did we meet? And it's almost 2 decades ago. And
numbers.
We were, But what it tells me is that partnerships and can the bonds that you make over ideas, over common missions can last years and years, and hopefully through your old age, and where you have kin who are your kin in many different ways. We have been very fortunate to have Doug also be a program manager for us when he was at DARPA for our haptics program. Those of you who know about the neurological prosthetics program, that was Doug. So Doug was a founding member of the Biological Technologies Office at DARPA. And Doug, you may not know this, but everybody who joins I-Cubed-R gets the DARPA Hellmeyer.
Oh, right.
Yeah, so that's what we pride ourselves on, and we hope we do not lose that we are fast, we are adaptive, we are moving very quickly on it, At CMU, Doug is co-director of the Neuromechatronics Lab. Lots of students, lots of postdocs and all of that. But he really is a man of the world with having made partnerships with industry, with the community, with the governmental part, but thinking of a future. So I won't take much longer, but welcome, and we look forward to hearing Chris.
Thank you, Renu, and thank you all for coming on this beautiful day. I think it's much nicer outside than it is in here, but I won't keep you for too long. It really is a pleasure to be here, and I just want to echo many of the things that Renu said. I think the best part about the academic life is the relationships you build, not only with your students, but your peers and your mentors, and certainly Renu and Jimmy have been both over the years, and so I definitely appreciate those relationships. I have a lot of slides, and I'm going to try to move quickly through this talk. Please don't hesitate to raise your hand and ask a question. We can pause for a bit as I'm racing through and answer any questions. I want to make sure everybody understands the different projects that I'm going to talk about. I'm going to keep everything at a very high level, so I won't get super technical. My goal is really to explain the concepts and hopefully illustrate the impact of the work that we're doing. Just want to start by showcasing our lab, and Renu mentioned the importance of convergence of ideas and perspectives, especially in research that's occurring at the further translation end of the spectrum. And so I draw students from across campus, neuroscience, almost half of the departments in engineering, physics, and so it's through that diversity of ideas that we're able to tackle problems at scale, as we mentioned. I'm also very fortunate to live in Pittsburgh, where our closest neighbors are the University of Pittsburgh and the University of Pittsburgh Medical Center. So the things we want to do in the clinic, we're able to do so only because of the partnerships that we have with the medical center community. And so we're very grateful for that. And I think most of the projects I'm going to talk about today involve partnerships with one or more of these people. Like Renu mentioned, it's important to focus not only on kind of the basic science, but to think about how to do engineering to support problems at scale. And so we try to span this full spectrum. We do better in some places than others, but I think I can't overstate the importance of really paying attention to the basic science. As engineers, we want to build devices that are maximally effective, but if we try to do so with a sort of black box approach, I think we're always going to fall short of that goal. And so really understanding what's going on in the nervous system in someone that's healthy and someone that's struggling with a disability, and then using that deep insight into those neural circuit functions, we can then engineer technology that can interact with the nervous system to maximize benefits. We do work with some companies, some big ones, mostly small ones, but that enables us to think not only about trying something new and hopefully showing that it's effective, but also paving a path towards getting those solutions out into the clinical market. Reach Neuro is a company that I formed a couple of years ago with some of my co-investigators at the University of Pittsburgh. We're working to develop a spinal cord stimulation system for people that have lost arm function due to stroke. So I should have disclosed that conflict of interest, but nevertheless, I think it's important to work with industry and create it when it doesn't exist. So I'm going to talk about 4 projects today. They're divided roughly into 2 categories. In the first pair of projects, I'm going to talk about technology that we're using to sense motor activity from somewhere in the nervous system of someone with a physical disability, and then use those signals, those indicators of what the paralyzed person is trying to do, read that data out, interpret it in a way that allows commands to be formed and sent to robotic limbs, computers, and other assistive devices, such that the user can regain independent function in the world. So sensing motor activity is a big part of what we do, but we also look at using technology to try to bring back function that's been lost. So bypassing a paralyzed limb is one thing, trying to reanimate that motor function in a paralyzed limb is another. So I'll talk about 2 projects in that space as well. So I'll start by talking about brain-computer interfaces, and then which are implanted devices in the work that we do. But we're also starting to develop wearable devices, which I think for many people that are living with paralysis, there's a lot of untapped potential there. And then on the reanimation side, we're not real exoskeleton experts in the lab, but having a home in mechanical engineering has afforded me the ability to work with really talented robotics students. And so we're starting to use robots as a way to reanimate function in the paralyzed hand. And then I'll close with our work on neurostimulation of the spinal cord, and specifically the sensory inputs to the spinal cord, which give us access to motor circuits that drive function in the limb and restore or improve that function in someone that's battling with chronic hemiplegia post-stroke. All right, so let's dig in. So everyone has a phone. We rely very heavily on digital devices, smartphones, tablets, computers, for more and more of our activities of daily living, right? And so when you lose your ability to use your hands, you lose or you sacrifice the ability to interact seamlessly with these devices. And so there are adaptive tools that are available to help people interact with digital devices, but those tend to be physical interactions. And so the traditional way we interact with our digital devices is through keyboards, mice, gamepad controllers, those sorts of things. All of these rely on physical motion, right? And so if you are paralyzed and you've lost that ability to interact physically with objects, then you're stuck. Your access is more limited. And so we and many others for years have been working on ways that sort of bypass the need for that physical interaction. If we know what message the person is trying to type, or we know what position on the screen the cursor needs to move, and we can get that information from the brain or from the muscles, then perhaps we can obviate the need for that physical movement. And so I'm going to talk about two projects. The first is using a device that's implanted in the brain to sense electrical activity that is generated in motor cortex and adjacent structures that's associated with attempts or intentions to move, and then converting that modulated neural activity into control signals. And then the second project is a wearable myoelectric interface project that really spun out of the work we were doing in the implanted BCI space, where we made a surprising discovery a few years. All right, so throughout I'm going to try to showcase or highlight the PhD students that have been working on these projects. So Nicole Chetty and Ariel Feldman will be graduating next year. They will be superstar postdocs if anyone's looking. Krithi Kakkar has one more year, so you'll have to wait for her. But the three of these students have really led the project that I'm about to describe. So before I get to that, I want to show kind of a deep cut from 15 years ago, where we really began our implanted BCI work. And so this is a study that is still ongoing at the University of Pittsburgh. Jen Collinger and Rob Gaunt are the two PIs that are leading the work. But I like showing this video because it really demonstrates the power or the potential of what you can do with an implanted BCI. And now there's a number of companies, including Neuralink, that are working to commercialize these types of technologies. But this is sort of a historical perspective on where we've come.
5 months after the surgery, we came back to see whether she would be able to control the robotic arm with nothing but her thoughts.
There's two connectors.
They plugged her brain into
attached to her skull. There's electrodes implanted in her brain, her motor cortex.
And straight down. And left to right diagonally. I can close it and open it. Then I can go forward and back.
That's just the most astounding thing I've ever seen. Can we shake hands? No, really.
Yeah.
Like, come right over here.
Yes, you can move
Okay.
there. Right, so your hand there we go. Oh.
Wow.
And I can do this one and like.
That's amazing.
So what's cool about that is just how effortless the activity seems to be for the participant's name is Jan. She's okay with us using her name. But she's using the arm like it's a natural extension of her body, right? She's not focusing all of her attention on the subtle movements of the arm. She's having this conversation. She's showing off a bit, right? And the reason it's so intuitive and easy for her to use is because we're able to measure activity at very high precision inside the brain. So we're recording the activity of hundreds of individual neurons in motor cortex. And we understand how those neurons encode messages that form the commands that generate our movements. And that was decades of neuroscience research that revealed and enabled us to build mathematical models that say this pattern of neural activity is associated with this speed and direction of movement. And so by putting those two things together, the technology that gives access to the signals and the deep understanding of how information is embedded in the activity patterns we're recording, you converge those two ideas together and you build technology that is really remarkable. Okay, so the downside though is that in order to get access to signals like that, you have to make a hole in the skull, you have to open the dura, and then expose the surface of the brain such that you can instrument it with the types of sensors that are needed to make those readings. And so this is a very safe procedure, I would say, so I don't want to overstate the risks here, right? Neurosurgeons are drilling holes in skulls, all day, every day, right? It's a very well-established, and I would argue a safe procedure. But it is still a very, that requirement for surgery is still a barrier to adoption, whether it be cost related or simply the icky feeling of having your skull open. It's a challenge that will limit the scalability of approaches like this. And so, always we're thinking about, well, what can we do to lower those barriers to adoption? And one way is to try to simplify that installation process. Instead of having to go through the skull and open the dura, what if we could access the brain through a less invasive way? And one way to do that is by using the bloodstream, right? If we can gain access through blood vessels, which of course, fan out throughout the brain, then maybe we can use those blood vessels as portals or entry points for getting into the brain. And so a company called Synchron came up with this idea 15 plus years ago at this point. I think they formed in 2010. So yeah, exactly 15 years, where instead of going in with microelectrodes through the skull, if we use an endovascular stent, which is delivered by a catheter, and if we put electrodes on the surface of that stent, then by going through the jugular vein in this case, we can gain access to the large blood vessels in the brain that are situated adjacent to primary motor cortex. So let me just play this little video if I can. There we go. And so this is what the device looks like. It's packaged inside a catheter. The catheter is delivered into the jugular vein, goes to the transverse sinus, and then when it reaches this part of the superior sagittal sinus adjacent to primary motor cortex, it's unsheathed from the cannula and then attaches to the vessel walls. And now, because we're sitting just inside that blood vessel and just outside of the blood vessel is the cortical tissue that we want to monitor, we can measure that electrical activity and route it out to an external device.
Sorry, Doug.
Yeah.
Can I go back to that other
Yeah, of
slide?
course.
And just for scale, could you, using the picture on the left, tell us how does the scale on the right relate to the scale on the left of what we're seeing in the blood vessels?
Macro scale, micro scale. So with penetrating microelectrodes, each sensor is about 10 microns in diameter at the tip. So very, very small. Each of those electrodes is positioned within a few hundred microns of individual cells in primary motor cortex. And at that close proximity, it's possible to read the activity of individual cells. Okay, but the further away from those signal sources that you get, the more mixed the message becomes, right? And so here we're within 100 or so microns, or let's just say a couple hundred microns of the sources. Here we're millimeter to centimeters away, right? So, we always use the stadium analogy. If you have a microphone and you're at a Razorbacks game and you have the microphone right up next to the person next to you, you can hear what they're saying. But if you take that microphone and you put it up in the nosebleed sections or in the Goodyear blimp circling above, the only thing you'll hear is sort of the cumulative activity, the roar of the crowd, the boos when the other team makes an interception, whatever it is, right? And so scale is super important. And so because of that, the type of information, the quality of signal we can access through that approach is far more limited than it is with this one. But the question is, how much do you need for the function you're looking to support, right? And that's really a patient-focused question, not an engineering-focused question. It should be anyways. Okay, so this is what the rest of the system looks like. So that's the working end of the device. It looks much like a conventional stent. It just has electrodes attached to the struts. The lead wires from those electrodes tunnel down through the blood vessel. It exits the jugular vein just above the clavicle. That bundle of wires then is routed under the skin to a telemetry unit that is positioned just below the clavicle. So we use that pocket, that subclavicular pocket, because it's such a standard placement for pacemakers and deep brain stimulators. So once the telemetry unit is under the skin below the clavicle, we use an external telemetry unit that attaches magnetically to the device. providing power to the implant and reading the data from it. That then connects to a computer where we were able to read and process the signals in real time. And so 4 years ago, we started a project funded by the NIH Brain Initiative. It's unfortunate that the Brain Initiative doesn't look like it's going to continue because it really has supported a lot of groundbreaking work, not only in brain-computer interfaces, but in many other areas of applied neurotechnology and neuroscience. Nevertheless, they supported us to do a 6-patient study in the US. Our primary focus was on people with ALS, so profound motor loss because of ALS. We did end up recruiting 1 person with brainstem stroke, but all of the participants in this study had very severe paralysis. And the goal was primarily to evaluate the safety of the device, right? This is an early feasibility study, kind of a first-in-human trial in the eyes of the FDA. And so the main thing we wanted to make sure of is that the device is safe, with secondary questions about efficacy. My lab, though, was primarily focused on the latter, the kind of efficacy-related questions. You know, how good are the signals that we measure? How stable are they over time? And how many degrees of freedom might one control with an interface like this? You know, unlike the intracortical BCI work that I opened the talk with, you know, there was decades and decades of neuroscience research done at kind of the single cell level, which really taught us a lot about the types of signals that we can measure and the ways in which we should interpret them. Here, because this is really a brand new interface technology, there were really open questions about the features of the signal that might be useful for encoding information. So that's where we started. And so to try to answer that basic question about how information is represented, we had subjects seated in front of a screen. Some of them were bedridden, some of them were in wheelchairs. But in all cases, we put a display in front of them and then prompted them to make attempted movements of different parts of their body. We would usually start with the legs because the position of the electrode array was closest to the midline, which should have the strongest representation for lower extremity movement. But we didn't only do legs, we did hands as well. In any case, we would prompt them to make these attempted movements, and we would alternate between periods of rest, so they're just supposed to relax, and go, where they're trying to attempt these different actions. And then we would look at the signals that were recorded during those rest and go periods and look for modulation in the signal patterns that was associated with the person's attempt to generate those movements. And so there's, these are very raw signals, so they look pretty noisy in this representation. But if we bandpass filter or do other feature extraction techniques on those signals, we start to very clearly see that as the person alternates between rest and attempted movement, there are clear changes in the signal properties. In this case, an increase in the signal power that is associated with their attempt to move. And because we have an array of electrodes, so there's not just one electrode, but in this case, 9 functional electrodes, we can look in that n-dimensional space where n is the number of channels and try to see just how separable are the signal features between these periods of rest and attempted movement. And so we just use a Euclidean distance, standardized Euclidean distance metric to quantify that. And so we can do that for different features. So in this case, we're looking at beta band signals and then looking at the strength of the signal modulation over the full span of the implant. Our first participant was only in the study for about 200 days before we had to explant their telemetry unit. The other participants were in for a full year. In all cases, the signals, the beta band signals were a little bit more variable. Participant 2, that they got quite small. Over time, there's reasons I can explain for that. But nevertheless, over the full span of the implants, we saw decent activity in most of the participants in the beta band. But where we really saw strong signal properties was in the high gamma band. So if we look in the high gamma band, what we see is that the signals are very detectable and very stable for the most part over the full year-long study. There's a couple of peculiar features in participant 6 where when they started the study, we could see that they were trying really hard. And so the signal modulation was really strong. But as they learned how to control the activity, it actually flattened off and always remained well above that.
Doug,
So, yeah.
are you decoding the direction of the movement?
In this case, we're only decoding rest from go. I'm going to talk about different subclasses of movement next. But yeah, we don't. In theory, we should be able to decode direction, but we don't. Here, it's just more of a switch or a binary output. Okay, and so for Mehran's question, we know we can detect movement. Now the next question is, how many classes of movement or different types of movement might we discriminate? And so to do that, we looked at how the pattern of activity that were recorded varied across the different parts of the body that the person was trying to move. And there's 6 different classes shown here. And if you just sort of look at this small and blurry slide, you can see that for the most part, the signals look pretty similar. There's some obvious, maybe more obvious differences on some of the electrodes, but overall, all of the electrodes or most of the electrodes seem to be showing signal enhancement during that attempted movement period. And it looks somewhat similar across the different classes of movement. But now if we break that signal down into a lower dimensional space, so instead of looking at it in 9 dimensions, if we project it down into a 2-dimensional space using linear discriminant analysis, and then color coding the different points on this graph to indicate the specific movement class, what we see is that now the pattern of activity associated with each of those different movement types is much more apparent, right? And so whether or not this means that we could decode 6 independent control signals from this interface or not, that's still an open question. But this does indicate that there is at least some task-specific modulation in the neural activity that we might be able to leverage. Okay, and now the last, I'm just going to show a demo video. So this is one of our ALS participants. I think he was number 2 in the study. He's fully locked in at this point, so he has no way to communicate with caregivers about how he's feeling. And so he's using the Stentrode interface here to fill out a pain questionnaire. So now he does, because he has no other way to communicate, he can use this to tell his family or his caregivers that, hey, I'm not feeling very well. Can you get me something? And so, a single switch in this case, but one that provides profound improvement in their quality of life, because now they at least have some way of communicating how they're doing. Quick takeaway here is that this is just an early feasibility study, 6 patients, but the early results are very encouraging. The company is working to make improvements to the device design, so I think the next iteration of this study will be even more promising. Okay, so now, so that was a minimally invasive. Yes, please.
What are the unintentional function of this device on other activity of the brain, either positive or negative?
So
I'm not talking about safety. I'm talking about other.
So I mean, one concern that is often raised is, does this create privacy risks? Like if somebody was able to hack into this device, could they learn something about the person's inner thoughts by reading out their brain activity and interpreting it in some malicious way? Is that what you're thinking about?
No. Well, that was a good thing to know as well.
Yeah.
If you put it in my brain, does it interfere with other function of my brain?
Not as far as we can tell, right? And so, I mean, we look for things like venous occlusion. Does the blood flow become restricted because this device is implanted in the blood vessel? The answer so far in all patients is no. Does the device move around over time? That too, the answer is no. In fact, it becomes encapsulated into the vessel wall or integrated into the vessel wall. So its position is very secure once that endothelialization process completes. Does it cause epilepsy? You can imagine that maybe it's an irritant, and so it's triggering unusual patterns of activity. We see no evidence of that as well. That might be hard to detect in people with ALS, but I think if there were epileptic activity being generated in the brain, we'd be able to see it in the electrical, because we're recording the electrical activity. So there's no evidence of that as well, So, question. All right. So minimally invasive devices offer, I think, tremendous opportunity to provide communication function for someone that is otherwise locked in. And so to go from no communication to even slow communication is a big step change and improvement. But it still requires a surgery, right? We still have to, bring someone to the OR. We got to do, bring them to a fluoroscopy suite to, where the electrodes can be delivered. There are still significant barriers to adoption, even setting aside the potential risks for safety problems. So wouldn't it be great if we didn't have to do any surgery at all? And so that got us thinking about ways in which wearable sensors might be used. And so Dalen Despradel is the PhD student that's leading this project. She's graduating also next year, but has her heart set on industry, so she's probably going to Apple or Meta, which she's done. Max Murphy is a postdoc, just turned research faculty. Can't have him because I want to keep him. Nikhil Verma, Luigi Borda are two PhD students. Nikhil's graduating next year. He would be a catch. Luigi's got a little bit more time. He would also be a catch. And Jen Shanahan is our coordinator. All right, so the idea of looking to myoelectric activity as a potential source of control in people that are paralyzed really ran counter to everything I had been taught since I started graduate school in '94. Back then I had joined Andy Schwartz's lab at ASU, and the reason they were putting electrodes in the motor cortex is because they thought, or everyone at the time thought, that was the best place or the only place to get motor control information from a paralyzed body. And so we had, after we had started doing the intracortical PCI studies in the lab at Pitt, one day we were like, let's just see if there's any muscle activity in the forearm. Because if the people, despite their tetraplegia, still have some ability to generate output from their paralyzed muscles, then maybe we can use that. And so we worked with Patel. They had developed this 150 channel sleeve electrode, not for measuring muscle activity, but for actually stimulating muscle activity. But nevertheless, it created this really powerful interface for blanketing the entire forearm with electrodes that we could use to try to measure the electrical activity of muscles in the arm. And so, again, we have participants sit in front of the screen. We give them an impossible task. Like in this case, we're asking him to try grasping with his hand. Hand is paralyzed, so it doesn't actually move. But during those prompts, we saw that there was clear myoelectric activity in the arm. So we thought, this is interesting. I wonder what we could do with it. And so, rather than just using the gross EMG, we decided that it would be better to study the activity, not at the whole muscle level, but at the single motor unit level. So using arrays of high density electromyography electrodes, we're able to separate out the individual action potentials generated by motor units when they're firing. And at this resolution, we can see what individual spinal motor neurons are trying to do as people make these attempted movements. And so here's just an example of what some of the motor unit action potentials look like. Here's a plot showing the spiking activity of those motor units during attempted flexion and extension movements of the wrist. And so you can see there's 7 motor units there. Some are active during flexion, others are active during extension. But what we see is that despite the paralysis, there's clear willful modulation of the motor unit activity associated with the action the person is trying to perform. And so we took that one step further and went to the level of the digits, where we asked the participants to try moving individual fingers in the hand. And again, because they have tetraplegia and it's motor complete, the fingers never actually move. But if we take all of the motor unit activity that we recorded during those attempted movements, sort of boil it down using principal components analysis, and then looking at where the population activity is distributed in this 3-dimensional space, we can see that there's very clear separation of that motor unit activity associated with each of the 5 digits. And if we use simple machine learning, we can classify with reasonably high accuracy which of the 5 digits that they're trying to perform. And one thing I want to emphasize here, in all cases, the participants never had any feedback of what they were doing. Right, so this is just purely open loop. They're trying to move their thumb, but the thumb's not actually moving. So their attempts or the pattern of activity that they generate from trial to trial is likely to vary because they're not getting that feedback that reinforces their actions. But in spite of that, the classification accuracy was pretty good.
Sorry.
Yeah, no,
What
please.
was the dimension of your space that you divided to three principal components, original dimension?
The original dimensions, I think we had 26 motor units in total when we across the 5 digits, right? So we start with firing rates for 26 motor units, and then do PCA on that. I think for the classification analysis, we used 8 of the principal components, not just 3. So I can only show 3 here, but there's a few other dimensions or components that contribute as well. Okay.
So the first 8 was sufficient to use most of that.
Yeah, that's right. And one of the reasons why we did that is we were trying to compare motor unit firings versus the raw myoelectric activity. That was recorded with 150 electrodes, so that's a much higher dimension even than the motor units. But to make it a fair comparison, we applied PCA to the EMG data, applied PCA to the motor unit data, picked the 8 best or the 8 highest principal components from each, and then did the classification. So, okay, I have 25 minutes left, so let me move fast. So that work caught the interest of some folks at Meta because they have for 6 or so years been developing a wristband interface, not necessarily for people with spinal cord injury, but for able-bodied users. But because this interface is able to measure myoelectric activity in a comfortable, wearable form factor, the program director at Meta reached out and was like, I wonder if this could be an accessibility tool for people that have limited hand function. And so she, suggested that idea to us, and we're like, sure, let's give it a try. And so we recruited, with their support, a total of 7 people with cervical spinal cord injuries. 5 of those have motor complete injuries, so 4 ASIA A, 1 ASIA B, and then 2 motor incomplete participants. So all of these people have varying degrees of tetraplegia. The A and B participants have really no measurable movement in the fingers, and the C and Ds have a little bit more. And so for these studies, we bring the participants in, we put the wristband on, and we map myoelectric activity in the forearm as they're making various attempted gestures, showing middle finger extension here. You can see that when they're prompted to move, there's clear bursts of muscle activity. And from that burst of activity and the array of recordings that we make, we can isolate motor unit action potentials from the array of recordings. And then we can also, because again, we have this ring of electrodes around the arm, we can try to estimate where in the forearm is the source of that activity. And so we use that as a bit of an anatomical indicator of which muscles might be involved. Okay, and so once we're able to isolate motor unit activity, then we couple it to a control input on the computer. Sometimes that control input is a mouse, like a button that the user has to click and hold. And they do so by increasing the firing rate above some threshold, holding it there, and then releasing it when prompted. So we call that the PR task, push button and release. But we also can use that activity in a proportional way to control the position of the cursor on a screen. So we show them a target somewhere away from the start position, and they have to move the position of the cursor by increasing the firing rate until they dwell over the target. So that's a FITS type task for those familiar with FITS tasks. And then what subjects prefer most of all is playing games. And so we can either use a button press function or cursor positioning function as inputs to very simple video games, which they find very fun. All right, so I'm just going to show some quick data here. So this is the push button and release task. Overall, the participants are able to do this task very well. Where they struggle is during that hold phase when they have to hold the firing rate above some threshold. They fail 40% or so of the time, but they have little or no problem asserting the button click. It's just the hold part that's a problem. What we see is that there's pretty clear evidence of skill refinement over the course of 4 sessions. So black shows their performance during session 1. Red shows their performance during session 2. This is the latency of the click. And so you can see that from session 1 to session 4, they're getting faster. So that's good. They're probably getting used to the task, improving their ability to recruit and control the motor units. And as well, the latency drops about 120 or so milliseconds from beginning to end. And then the other thing we wanted to know is, how does this type of control interface compare to what the physical interfaces that they typically use? Because most of these participants are still using a smartphone or a touchpad or something. And so we can measure the latency for how quickly they can use the touchpad to generate a click and compare that to how quickly they can generate a click with their EMG. And the EMG definitely has approximately 100 millisecond advantage. The other thing that is that was a bit surprising to us, if you notice here, I've grouped the data points by the impairment level, or the Asia impairment score, where A and B are the motor complete and C and D are the motor incomplete. And we can see no real difference between the motor complete and motor incomplete participants. So the severity of their injury doesn't seem to influence the controllability of the motor units that they're still able to recruit. And I think that's super important. All right, so the other type of task that we did was this fits-like task, where we put a target on the screen. The size and position of the target varies from trial to trial. There's a small target close to the start position, so they have to increase the firing rate to reach that target zone, hold it there for a full second. That's usually the hardest part of the task, especially for the small targets. And then once they hold it for a second, then then the task is complete. And so here we have two target distances, two target sizes. So the index of difficulty for the task varies with the distance away that the target is and the size of that target. For the far small targets, their success rate is only about 64%, but for the near large targets, it's almost perfect. And so this isn't surprising. This kind of matches standard fits-like tasks, but nevertheless, overall, the control is pretty good. If we look at the success rates, again, comparing across impairment levels, the participants with motor complete injuries do about as well as those with incomplete injuries. If we look at their improvement over time, here selecting only the motor units where they had kind of low performance at the beginning, success rates less than 80%, that even with those poorly controlled motor units at the beginning, they're able to improve their performance over time. So practice does help them develop improved strategies for controlling motor unit activity. And again, if we compare motor complete and motor incomplete, they improve about the same amount over that time. So this is just a bit of an anecdotal result, but one of the problems or challenges that we have using myoelectric activity is that many of the users or potential users will have spasticity or involuntary muscle contractions in the arm. And obviously that's going to create problems. If we're trying to read out only the voluntary output from the nervous system, but there's this background involuntary activity, it will contaminate the recording. And what we found, let's see, here we go, is that, so here we have the participant doing this 1D fits task. The firing rates for the target motor unit are shown at the top. And the control of the motor unit is basically unaffected by spasms that are occurring in other parts of the arm. So if we wait just a little bit, you'll see a spasm occurring. So there you can see the burst of activity on the off channels, but no effect on the target motor unit. So this is, I think, argues for a potential advantage of using single motor unit activity as the control signal. I'm just going to skip through these. I have a bunch of game videos, but participants really love the video games part of this. And especially in this case, we had a young man, he's 21 years old. He really wanted to play video games with his mom, something they had done before his injury. And so we created we call it Luigi Kart because we have a Luigi, we don't have a Mario, and we don't have copyright. But anyways, we created this driving game, a two-player driving game, where the participant was able to play against his mom side by side. And I think the audio was turned down, but they really, really enjoyed it. Yeah. All right, I need to speed up. So the takeaway here is that even with wearable, wholly non-invasive interfaces, for a lot of people with spinal cord injury, I think this is a viable option because despite the paralysis, the likelihood that there are literally no surviving motor units is low. All right. So now I want to shift gears and talk about reanimating function in the paralyzed hand. And we were talking about master's students yesterday. Zach and Elihu are two master's students that are graduating in May. Write their names down. They are spectacular. All of the stuff I'm going to show next, at least on the exoskeleton side, are their creations. Jonathan Shogach is a Ph.D. student that will be graduating next year, but wants to start a company. Krithi, you've already heard about, and Max as well. All right, so this is a project that started not because, well, I've certainly been fascinated with robotics for many years, but I never had the guts to try to build one. But so many of our participants that were coming into the lab for this EMG study were like, can you get us a robotic exoskeleton? Because I really want to move my hand again. Like they like being able to play games and stuff like that, but what they really wanted was to feel the movement of their hand again. So we're like, sure, why not? So Zach and Elihu joined the lab a year ago, and they're like, yeah, we can build a hand exoskeleton. Just get us a 3D printer, and we'll take care of the rest. So my sole contribution to this is I bought them the 3D printer. So the current version of the Exo has 7 degrees of freedom. So there's a 2 degree of freedom thumb. There's single degrees of freedom at each of the other digits, and then the wrist as well. And so this is one of our participants using the hand Exo to perform a pick and place task. Right now, the control interface is super simple. It's just a button, an array of buttons that he picks to pick which grasp he wants to generate. But with the exoskeleton, he's able to now, close his hand on the object. The proximal joints on his arm are functional enough that he can reach and then release the Exo when he wants to. And so you can see without the exoskeleton, he really struggles to do the task, but with the Exo, he does pretty well. And so one of the things that is up next for this is to use EMG, high density EMG, as a way to sort of get rid of that button pad, and instead have him form the control commands for the Exo using their own EMG. And so that's work in progress, but at least from a decoding standpoint, we're able to decode with pretty high accuracy. I don't even know how many gesture classes are shown there, but a sufficient number of gesture classes to make the exoskeleton useful for the participant. Now, because we're using an exoskeleton to impose movements of the hand, it starts raising questions, or at least for me, about what effect that motion will have on the muscle activity that is being used to command the exoskeleton. Right? We know in our normal movement that proprioceptive feedback from the muscles plays a critical role in shaping the motor output to those muscles. And so when we're controlling computer, cursors and things on a screen, there is no somatosensory or proprioceptive feedback. But what's going to happen when we start moving the joints and stretching the muscles that we're using to control the task? So Krithi Kacker is leading this study where we're using the exoskeleton to move the wrist back and forth. We have the participants move as far as they can without assistance. And so they measure the EMG during that period. And then we turn on the exoskeleton when they reach their limit and see what happens when the robot finishes the job. And so I think this is a video that shows what that looks like. So they're going to extend a little bit with their hand. You can see they're pretty weak. And then the motor turns on and helps them finish. And so if we look at the motor unit activity as they're trying to do that, what we see in the yellow, that's the unassisted phase. There's clear increase in motor unit activity as they're trying to extend the wrist. But then when the exoskeleton turns on and helps finish the task, we see in some cases an enhancement or a reduction in motor unit activity. The motor unit at the top only appears during that assisted phase. So there are clear effects of the movement on the motor unit activity. This is very early days, and we're trying to figure out what it means and how can we actually potentially leverage that enhanced motor unit activity, maybe for rehabilitative purposes, or at least be able to accommodate it when we're doing the decoding. Okay, 10 minutes left. Let's skip over this. Okay, so the last project is not using robots, but using electrical stimulation to try to improve function in the paralyzed arm. And here we're working with people that have chronic hemiplegia post-stroke, so they're at least a year or more out from their stroke, and they have profound impairment in one of the arms. I've talked about everybody but Prakash and Lauren and Omar. Omar is now a postdoc in Copenhagen, but he's going to be looking for faculty positions next year. Lauren and Prakash are going to be graduating next year both are industry known. All right. So, so the problem in stroke is that the connections between the sensory and motor areas of the brain become somewhat disconnected from the sensory motor structures in the spinal cord. And as a result, there's obvious weakness. I think that's the thing that most people see. But what you may not see is the spasticity that is produced, the impairments to sensation, which may not be obvious. You may notice abnormal coordination strategies when the person's actually moving. But the bottom line is there is a large and distinct set of problems that are all related to sensing and control in the arm that need to be corrected if we want to restore function. And historically, the main approaches to trying to reanimate function in the paralyzed limb have been to not target the controller, but rather to target the effector, right? And so functional electrical stimulation, which many in this room are experts in, that's really a compensatory approach to stimulate missing input to muscles, right? So the output from the spinal cord is too weak to produce action and a sufficient action in the muscle. Let's compensate for that by electrically stimulating the muscle directly. That's one word. That's one approach. It's effective. The other approach is to sort of bypass the muscle altogether, use an exoskeleton, apply an external torque using a motor. That too, compensatory approach. But neither of these really targets the right box, in my opinion. Right? The box that we want to target is the brain or the spinal cord, where that control signal is being formed. And so if we can do that, then maybe we can do a better job of reanimating or restoring natural control of the many muscles of the body that have to be moved to produce purposeful. All right, so this is our approach for doing that. So rather than targeting the muscles or the effector side of this, what we're doing is we're targeting sensory inputs to the spinal cord with the goal of changing the sensory motor networks in the spinal cord. And I'm hand waving here on purpose because I don't have time to go through the mechanisms. But the bottom line is what we're trying to do is change the relationship between the weak descending inputs from the brain and the output that goes to the muscles. And by electrically stimulating sensory pathways that are projecting into the spinal cord, we see an improvement in the output to the muscles. So this is what the approach looks like. Oh, I skipped right over that. So I think I might have to click on this. There we go. So we're using standard epidural spinal cord stimulation electrodes. These are delivered by a needle, so another minimally invasive approach. The needle accesses the epidural space of the spinal cord. We thread the electrode along the epidural surface. Sorry, my daughter is calling me, and I hope it's not urgent. And so with that array of electrodes, we can electrically stimulate at different levels of the spinal cord. In this case, we're in the cervical spine because we're targeting the upper extremities. And so each of those electrodes provides an access point for stimulating different parts of the cervical cord. And so I'll skip through this. So what we do is at each of those sites, we electrically stimulate one contact at a time, and we record responses in the muscles of the arm to see which muscles are affected by each electrode that we're stimulating. And so as we go from the top or the sort of base of the skull to the top of the shoulders, we can see that the site of activation in the arm changes from shoulders down to forearm. And so once we have that map, we can pick specific channels that target muscles that need help. In a lot of cases, it's triceps muscles or muscles that extend the wrist. In other cases, it's as you'll see in this case, muscles that are needed to perform a grasping action with the hand and flex the elbow. We can pick a set of electrodes, find a set of stimulation parameters that work to sort of boost function in the arm, and then just turn it on and leave it on. The stimulation by itself does nothing. Like if the person's resting, the muscles aren't going to be twitching. But because we're changing the gain of that cortical spinal circuit, the arm is much more effective at producing movement in the presence of stimulation. So now I'll just play this video. So this woman was 9.5 years out from her stroke when she entered the study. So her left arm was pretty impaired. This is, I think, week 3 of the study, 4 weeks in total. You can see she's struggling to hold the handle of the fork, and so it keeps slipping out of her grip. She has to rely on her right arm, which is the unaffected side, to help get the job done and for each of the steps of this task. The blinking lights are just EMG sensors, so they're not really part of the stimulation. But now she has a hold of the food, she's holding the fork, but because her elbow and her forearm are too weak, she can't actually bring the fork all the way to her mouth. Okay, and so now we're gonna turn on stimulation for the next sequence. We're picking 2 channels here, 5 minutes, okay? And so now we're targeting muscles in the arm and the hand. And you can see that her grip strength is markedly improved. She has a firm grip on the handle. She can supinate her forearm, and she can flex her elbow now to bring the food all the way to her mouth. And again, it's just tonic stimulation. All we're doing is we're biasing those circuits, but doing so in a way that improves the output, the control signals that are going out to the muscles. Okay, we have a couple of papers that are in preprint form. One actually just posted yesterday and really digs into the mechanisms. There's another one by Luigi Borda that focuses on this mechanism specifically. One of the really interesting things that we found is that going into this, we knew that we would be able to facilitate activity in muscles that we were targeting. So like we often target the triceps muscles. And we can see that if we look at the effects on motor unit activity, the whatever muscles we're targeting show increased spiking activity in the motor units. What we didn't expect to see is that that same stimulation would affect not just the muscles that are producing the movement, but it suppresses activity in muscles that are opposing the movement. And so Luigi's got a really nice study that shows that, and the modeling paper we put out yesterday treats it as a PD control system. And again, what we see is that the dominant effect of spinal cord stimulation is less about boosting weak muscles, and it's more about suppressing spastic or overactive muscles. So that story is still unfolding. All right, I don't think I have to summarize. I mean, we like technology, but our purpose is really to use it as a way to bring back function to people that have become paralyzed. And we think by doing so, we can greatly increase their independence and hopefully their quality of life along with it. With that, I'll take any more questions.
Okay, the tour de force. Okay, questions?
Oh, I'll ask one. In your research with your stroke patients, did you have any that say received stroke-related drugs very quickly after their stroke versus those that didn't? And did you do differentiation between that in your testing?
So because we're only looking in the chronic stage, and I think the nearest one was like 2 years post-stroke. So whatever medication they were on, kind of shortly after their stroke, they were probably off by this point because spasticity and things like most of the medication that they are taking at the phase when they enter the study are antispastic medications. And those, we used to ask them to stop taking them because we didn't want it to interfere with the results. We don't think that that's even a problem. Right? We don't want them on Botox because we don't want the muscles to be completely paralyzed. But if they're taking baclofen or something, and it's important for them, then we try not to interfere with that. But other medications, I don't know if there's a specific one that you have in mind, but it's really the antispastics that we are concerned with because it might interfere with the mechanisms we're trying to exploit. Yeah.
Similar question. I'm wondering when somebody had a stroke, they send it to physical therapy, etc. So if this device is going to, in long term, is going to improve along with, or does it interfere with physical?
Very good question. So when we started this work, we were trying to decide, are we building a prosthesis, something that people would have to rely on all day, every day for the rest of their lives, right? Because if it's necessary to provide the function, that's a different use case than if it's a restorative or a therapeutic device. And so we were confident that we could at least get that assistive effect, the prosthetic effect. We weren't sure about the restorative piece because that, there's it's a more complicated study design. In the seven patients we've done to date, we haven't really done anything that would qualify as rehab specifically. Now the participants are coming in, we're fiddling with stimulation parameters. They're doing lots of things with their arm that they wouldn't otherwise be doing. So maybe that increased physical activity has a therapeutic component to it. It almost certainly does, but we haven't had a deliberate therapy yet. In the next phase of the study, which will start in January, we're going to do chronic implants, which will give us a much longer period to study their response. And we're going to start with a 6-week rehab only phase, right? So, we don't expect to see much gain, but we expect to see some gain during that rehab only phase. But we'll see where they plateau. And then the question is, if we do rehab plus stimulation, how much better can they get? And hopefully, much. But let me just say one more thing. So despite our lack of effort to produce therapeutic effects, all of the participants do show a measurable improvement over their baseline in function. Whether that's how much of that is stimulation mediated or just versus just that increased activity that they're doing, still an open question. We didn't design the study to isolate that, but it is pretty interesting to see just how much better there are moves at the end.
Thank you.
Yep.
You had mentioned that, Meta was interested in that sort of wristband technology primarily for Copley patients. What, I guess maybe you can't say so, but what is the expected benefit or use, I guess, of this technology in health care?
So they have a brand new product that they just released about a month ago. So they have AR glasses that have a display inside. There's an audio player, internet connectivity, so you can do web searches and things. And so it's a gesture interface for controlling the features of those glasses. And I think they're envisioning a whole new ecosystem of devices where you're wearing the internet essentially, and you need a convenient way to control the functions or control the inputs needed to operate in that space.
Wonderful, that was as expected. You with the non-invasive muscle interface, you quickly put something up to say that you could do a spatial localization of the sources.
Yes. It's purely geometric. There's no forward model of the tissue properties or anything. It's just triangulation.
Was that used at all?
No,
that was just
we look at it, right? Because when we're having participants do wrist flexion tests, and again, because when there's no movement, you never really know, are they doing the right thing, right? But if we can see that the activity, that the strongest activity is coming from the opposite side of the limb where you expect it, then you start becoming suspicious. Well, are we looking at the agonist or are we looking at co-contraction of the antagonist? So that's why we look at it, but it's purely qualitative.
Okay. And then you mentioned that with you didn't see a differentiation across severity level.
I overstated that.
Okay.
Where we do see a difference, so in the tasks that I showed, what I didn't show was the 2D task where they have to control 2 motor units at the same time, one to move in this direction and another to move in this direction. Turns out that regardless of the impairment level, if we're using 2 motor units that are closer together, it's hard, and this maybe isn't surprising, but this is what the data bore out. It's harder to isolate or control their activity independently. The further away, the further separated they are in the arm, the more accurate they are in performing the task. And in the motor incomplete participants, we saw that they were better because the separation was greater. There's just more motor units available in the less impaired arm, and so we were more likely to grab 2 motor units that were further apart.
Okay,
So
kind of good, and that kind of gets to my question. I was wondering, did you see any fundamental differences in the properties or how your algorithm got the control signal out of the set that you're recording?
So that's going to be paper number 2 in this series, because I think that's really where the interesting questions are. It turns out that task control is better the higher the steady state firing, so the bigger the dynamic range of the motor unit. If the participants can only control firing over a range of 0 to 5 spikes per second, they're going to do poorly on the proportional control task. But if their range is 0 to 25 spikes per second, they do great. Right, so there are, firing property, like the firing rate statistics matter, but we didn't use those when we were selecting motor units, in this study, because we're kind of figuring it out as we went along. But looking back at the data that we collected over the past 1.5 years, that seems like the firing rate properties seem to matter a lot. And it probably, it should make sense, like the recruitment order, all of that, stuff does matter. But
And if you stimulate the spinal cord with your electrode, then you'll get that prosthetic rates you're looking for.
we tried to do that with Dimitri using TSCS, and we were working with Dimitri Sayenko. And in one of the 5 subjects we were able to show that we could decode finger movements more accurately with TSCS on, but we have a lot more work to do to really make strong claims about that. But in theory, it should, right? Like if you can boost the natural control functions of the nervous system using spinal cord or deep brain stimulation, then yeah, in theory, it should boost their controllability.
Making me think about some older rat studies that we had done with spinal cord injury, and right after this is incomplete spinal cord injury, right after that, if you get them to do treadmill therapy, then it is better than not doing any therapy. They'll get some recovery, right? Yeah. If you just we had actually used FES as a model to stim, but when you do movement therapy with that, then you get better. But actually what the overall story was that when you do FES early on, it actually advances the recovery that you get if you were to just do treadmill therapy. And so I was wondering about your stroke study where your design is first do that and then put the other part. And
so should we be stimulating during the acute phase, not the chronic?
Chronic phase, and would that actually have enhanced their recovery, which is what because we had started out with a different
I completely agree. I think that is something that must be done at some point. The FDA is likely going to make us focus first on chronic, make sure it's working well there, and then see if we can start shifting the implant date earlier. Because if you can't, like, one of the big problems is the compensatory behaviors that people develop over that year-long phase of their acute and subacute recovery. And so if they're learning bad habits over that period, then it might be hard to correct them, even with stimulation. And then the other thing that happens, and we saw this in one of our participants, that she developed contractures. And so that's a mechanical problem that our stimulation isn't going to touch. And so had we intervened earlier before those contractures developed, probably her outcomes would be much better.
And related, has anybody looked at what kind of neurotrophic factors are being, there's the endogenous release to promote recovery. Yeah. And I think that was our theory, was that we're actually boosting that neurotrophic factor by this.
I think Martine's lab, he does a ton of spinal cord stimulation, mainly after spinal cord injury, mainly in the lower extremity. But I think he's looked, at a more detailed level than we have at this point. But yeah, I mean, it's a more complicated story than that simple little reflex circuit that I showed you.
Oh, but it's cool. But I think the more important part is you're saying it is inhibiting the inhibitory.
That was the thing that surprised us. And, Omar's paper is now, it was posted yesterday on medRxiv, and it looks for the motor control, for the classical control people in the room. I'm anxious to get your feedback. It shows really nicely that the dominant effect is on what we call the derivative gains for the antagonist muscles, which basically act as brakes. And we sort of had the insight because we were watching the participants, try to do this simple reaching task with their arm. And, and their triceps was weak, but it was strong enough to be able to extend the elbow. But yet they struggled. And moreover, they ratcheted, so they would start moving, then they would pull back, then they would move again, then they would pull back. And we're like, problems in the biceps, guys. And so we modeled it, and it does seem, and it's consistent across participants.
I think perhaps everybody didn't catch that, but that you not only do experimental work, but you do a lot of computational modeling, and that is part and parcel of. So, any more questions? Yes.
Have any of your study participants had cerebral palsy, or do you think the devices will benefit them?
We hope so. There's a group at another institution that has funding to do a study in CP, and our company is working with them to run that study. I don't know when it's actually going to start, but hopefully sometime next year. But yeah, the hope would be that we would see similar effects in people with CP. Now, again, I think inclusion criteria are gonna be really key, right? Because we don't think this is gonna work for everybody. And so we for this first phase of the study, we selected people with over a broad impairment spectrum, so from very severe to less severe. The more severely impaired they are, the less gain we can see. And that isn't at all a surprise, but we wanted to check to see like where should we set that cutoff. Because again, like with this approach, we're amplifying spared function. The less spared function there is, the less we can do about it, right?
Thank you so much.
Good luck.